All right, today we're just going to take an interesting look on some of the characteristics or the patterns of polynomial functions. We'll start off looking at a linear function, then a quadratic, then a cubic, and perhaps a fourth degree. Really, the point I'm trying to make will be fairly evident when we see get up to the quadratic. But I think it'll be useful to at least go up to a cubic, and if not beyond, to kind of bring the point home. It's just a very interesting pattern that's going to occur here. And it's kind of something I've looked at since I was a kid. I always found it very interesting. So let's kind of just look at it. All right, so I'm going to just write some linear function. And so let's say f of x is, say, 5x plus 3. And then I'll do a table of values. And to make this more evident, in my table of values, I'm just going to differ the x values by 1. So it'll be consecutive integers increasing by 1. So I'll start off with 0. And f of 0 is 3, and then I go to 1, and f of 1 is 8, and then I go to 2, and f of 2 is 13, then I go to 3, and f of 3 is 18, and then lastly I go to 4, and then f of 4 is 23. And so what I want you to notice about this is the difference in these f of x values is constant. 5, 5, 5. And that number is also equal to the slope of this linear equation. And that's because this difference is really the rate of change of these guys. So, if you think of the average rate of change of a function, it's f of b minus f of a over b minus a. Well, in this case, b minus a is going to be 1 because these are consecutive integers. Like b minus a is like, 1 minus 0 or 2 minus 1. Etc. So, it's 5 over 1, 5 over 1, 5 over 1. Again, the average rate of change or the rate of change of a function is very similar to the slope. So it's fairly obvious that the rate of change will be equal to the slope. I could do subsequent examples of linear functions. Let's just do another one real quick. And so let's say g of x is 7x minus 4, table of values x, g, just real quick, when x is 1, we get 3, 2, 10, 3, 17, 4, 24, and we can do the difference on those, 7, 7, 7, slope is 7. So, this is fairly obvious and not really groundbreaking because, again, when I'm doing these differences, it's really the same thing as the average rate of change. And so obviously that would equal the slope. Now, let's look what happens when it's not linear, however, because if it's not linear, it's not really prescribed slope per se. Well, you could say there's a slope, but that slope would vary depending on the value of x. So let's say let's call this function, let's go back to f of x. And let's say it's 3x squared plus 2x plus 5. And again, let's go with table of values, x and f. And here I'm going to need maybe a few more values than I've been using to bring this point home. And so I'm trying to make this arithmetic here easy. So I'm going to start with 0 and work my way down. Of course, f of 0 is 5. And f of 1, I just add up the coefficients. That's 10. And then, oops, didn't mean to do that. All right, kind of hit the button on this pen that I didn't intend to hit. And then f of 2 now, it's going to be a little bit of work here. So I'm plugging in 2 for x. 2 squared is 4 times 3 is 12. 2 times 4 is 4, 12, and 4 is 16, plus 5 is 21. And now we'll plug in 3 for x. 3 squared is 9. 9 times 3 is 27. 3 times 2 is 6. 27 and 6 is 33, plus 5 is 38. And then let's go do another one. 4. 4 squared is 16. 16 times 3 is 48. 4 times 2 is 8, 48, and 8 is 56. 56 plus 5 is 61. And, I'm not trying to do these super fast, but I'm trying to get through the video. And, I'm capable of making a mistake and doing this through arithmetic. All of them seem fairly simplistic, but the one with 4, just want to double check before I go on and make sure the number is accurate. So I'm just going to reevaluate just to make sure it's correct. So again, 4 squared is 16. 16 times 3 is 48. 4 times 2 is 8. 48 and 8 is 56. 56 plus 5 is 61. All right, looks good. So now I'm going to get the differences here like I did before. And so this is 5 here, and that's 11 there, and that's 17 there, and that's 23 there. So if you notice in this case, those are not the same. Obviously, they're not the same. But if I now get the differences of the differences, they tend to be the same. So this would be 6, and this would be 6, and this would be 6. So really a way you can determine the degree of a polynomial if you're looking at a table of points where the x values differ at a common difference. If those differences become constant on a second level, it's a second degree polynomial, which we call a quadratic. If they're the same on the first level, it's a first degree polynomial, which we call linear. And third is cubic, and fourth, et cetera, so forth and so on. But I also want to think about like the fact that this distance is 6. Like, why is it 6? We knew why the number was for the linear. It was the slope. So what does this 6 represent? Because again, like the graph of this guy is, something, it's a parabola, something like that. And to think of its slope, the slope varies at the different values of x. Like when x is whatever this is, that's the slope, some negative number. But here, the slope is there. So it has a varying slope. It has different instantaneous rates of change. So where does this 6 come from? Well, if you look at it, and so if you have an understanding of calculus, this should be fairly clear. If I look at this guy, if I take its first derivative will be 6x plus 2. And if I take the second derivative, basic derivative that makes it a constant, I get 6. So what you'll notice on these quadratic functions, when I get to the second level, that second level will be equal to the second derivative, the derivative that makes it constant. So let's look at another example. All right. So I'm just looking at the time. Let's say this is some quadratic function, f of x. Let's do it like this. 5x squared plus x plus 2. So if you look at this, the second derivative, I think you can clearly see the second derivative is 10. So when I do the second level of the differences, I should get 10. And that should be easy to see. So let's go x and f. At first I started varying what this function was. It went from f to g. Now I've just been doing f. I think I just keep it f for the rest of the video. No need for the variance. All right, so let's start off again. The easiest number to plug in is 0. F of 0 is 2, obviously. And then f of 1 is the second easiest. F of 1, I'm just going to add with the coefficients. That's going to be 8. And then f of 2, now it's going to be a little bit of a calculation. Understanding how this operates, I think I can say the number is going to be 24, but let me go ahead and plug it in and do the work and see what happens. So 2 squared is 4. 4 times 5 is 20. And 20 plus 2 is 22. Plus 2 is 24. So it is 24. And then when I plug in 3, just based on how the pattern should go, I should get 50. And again, now let me talk about how I'm getting getting this number 50 before I actually even plug it in. It's kind of based on what we just said. Again, here I saw this difference is 6. So if I understand that the differences of the differences are going to be 10, then this next guy should have a difference of 16. So when I got 24, all I did is added 16 to 24. And then this next distance should be 26. So when I'm saying 50, all I'm doing is adding 26 to 24. And in fact, for 4, I'm just going to add 36. And so 4 should be 86. I haven't plugged it in yet. So I will plug these in just to make sure they work, but me understanding the pattern. And it's a beautiful thing about mathematics, how mathematics allows you to do less work when you understand patterns. Really, that's the beauty of calculus and other higher levels of mathematics. The recognitions of the patterns makes you do things that were more tedious very quick. So quite honestly, me understanding how this works, I know 50 and 86 are going to be the right values, but for the sake of the audience, let me go ahead and plug it in so all my non-believers understand that this really works. All right, so I'm going to plug in 3. All right, so I'm right here. So 3 squared is 9. 9 times 3 is 45. And then 45 plus 3 is 48. And then plus 2 is 50. Obviously, it works. Let's plug in 4. So plug it in right here. 4 squared is 16. 16 times 5 is 80. And then 80 plus 4 is 84. And then 84 plus 2 is 86. So obviously, you see that works. And then 10, 10, 10. And again, if we wanted to get, f of 5, we would add a 46 to that. That would be 132, and we can continue on like that. So it's a pretty neat deal. So let's go to a cubic function. And I said I might go to a 4th degree polynomial. I'm not looking at the time. This video is right now at around 12 minutes. And I like to keep my videos between the longer ones, at least no longer than 15 minutes. So doing the 3rd degree will take me right up to that point. So let's do a 3rd degree polynomial. So let's say f of x. And I don't want to make it too bad. I want to make my arithmetic fairly easy. Is 2x cubed plus x squared plus 2x plus 1. And now, so if we follow what we were talking about with the quadratic and our understanding what we always spoke about, when we do the third differences, they should be the same. And then it should be really equal to what the third derivative is. So the third derivative of this guy, and you can just look at it, as I get to the third derivative, all that stuff there is going to cancel out. So really, I'm just going to really concentrate on this term. So the first derivative, it would be 6x squared. And then the second derivative, it would be 12x. And then the third derivative, it would be 12. And so that's what I'm expecting to get when I do the third level of differences. Because I have to get to the third level, I'm going to need more numbers so I can do that subtraction. So I'm going to have to kind of write a little bit smaller so I get more numbers in. So this is x and this is f of x. All right. So again, we'll start with 0. F of 0 is 1. And then we'll do f of 1. F of 1, again, I'm just adding the coefficients. That's 2 plus 1, that's 3. And then 3 plus 2, 5, it's 6. And now the rest of these are going to be a little bit of work. So we're going to plug in 2. All right. So I'm right here. 2 cubed is 8. 8 times 2 is 16. All right, that's 16. Now I'm here. 2 squared is 4. 16 and 4 is 20. Now I'm here. 2 times 2 is 4. That's 24. And then plus 1 is 25. Okay, it's 25 there. Now I'll plug in 3. So here I'm right here. 3 cubed is 27 times 2 is 54. 3 squared is 9. 9 and 54 is 63. 3 times 2 is 6. 63 and 6 is 69. And then plus 1 is 70. And now let's plug in 4. So 4 cubed is 64. 64 times 2 is 128. 4 squared is 16. 16 and 128 is 144. 4 times 2 is 8. 144 and 8 is 152 plus 1, 153. You see I'm being pretty calm here because there's a good chance that I can make a mistake here. I think I'm doing okay. Now let's plug in 5. So again, I'm right here. 5 cubed is 125 times 2 is 250. So 250. 5 squared is 25. 250 and 25 is 275. 5 times 2 is 10. That's 285. And plus 1, 286. All right. I think I have enough numbers to do my analysis. So I'll do the first difference, which is not going to be the same. That's going to be 5. And that's going to be 19. And that's going to be 45. And that's going to be 83. And that's going to be 133. And then I'll do the second level, which also won't be the same. And so this will be 14. And this will be 26. And this will be 38. And this will be 50. And now, if you look at the third level, the difference between 14 and 26 is 12. 26 and 38 is 12. 38 and 50 is 12. So it works. So what I illustrated is really not necessarily something to help you solve problems. There are some applications of this in evaluating functions that can kind of make it easy. I think you saw as I was doing a quadratic, but really it's really not nothing to help you solve anything. It's really just a very interesting uh, pattern, if you will, or characteristic of polynomial functions. Hope you enjoyed it as much as I did. We'll see you next time.